everyone, how's it going? My name is Liz from the growth team at Divinity Foundation, and welcome to Community Conversations. So this is an opportunity for you, the community, to ask your questions to contributors within the internet computer ecosystem and get a chance to interact with them. So state sync enables replicas that fall behind to catch up to the subnet's most recent state. In this talk, Stefan Schneider is going to go over an overview of recent improvements to the state sync protocol that help to ensure that the rapidly growing number of canister smart contracts and their memory footprint can be handled by the internet computer. So I'm going to throw things over to Divinity software engineer Stefan Schneider to take things away. Thank you, Stefan.
Thanks, Liz. So I'm going to talk about some recent changes we did to a part of the internet computer called state sync. And the end result of it is that the internet computer is a bit more scalable than it was 2 months ago and a bit more robust. So I want to take the opportunity to kind of share the details with you, the community. So the plan for today is, first of all, I'm going to explain what state sync even is. It's not really a user-facing component, so I don't really expect you to have heard of it. So I'm going to start at the beginning. I'm going to explain what it is, how it works, and most importantly, why it needed to be improved. And then in the second half, I'm going to go over the individual optimizations that we did. There are 8 in total that I'm going to mention. Individually, they are each quite limited in scope, but together they have quite an impact. But before I explain what state sync is, I wanted to talk a bit more about why we're having this community conversation. On the one hand, state sync is something that you should not have to worry about, neither if you're developing canisters nor if you're a user of canisters. It's just something that should work in the background. On the other hand, we have been continuously working hard to improve the fundamentals of the internet computer. So its performance, scalability, how robust it is. And in the last few months, that meant, among others, improving state sync. And I think it's important for us to try to be as open as possible about the development of the internet computer, because in the end, by the end of the day, it's a community-led project. All the important decisions are made by the NNS. And if you have a neuron, you might have well voted on these changes that I'm going to present today. And the other reason why we're having the talk now is because it hasn't been quite the hidden feature that it's supposed to be. There were some problems with state sync, and they were noticeable if you were on the wrong, if you had a canister on one of the subnets. So to understand what state sync is, I'd like to go over some of the basic design of the internet computer first. So the internet computer is split into subnets. So in fact, if you deploy a canister to the internet computer, what you're really doing is you're deploying it to one of its subnets. Each subnet consists of a number of replicas. So our smallest subnets at the moment have 13 replicas. Our largest, which is the NNS subnet, has 40. And these replicas are run by independent node providers. They are independent from each other. They're also independent from Divinity. And in fact, these node providers are the only ones who have physical access to the nodes, for example. The basic idea of a replica is that it replicates the subnet state. So all the replicas have the entire subnet state on their node. So for the subnet state, I'm mostly going to be talking about the subnet state singular, but as a mental model, it might help to just think of it as the collection of the states of the canisters that are on a subnet. So it contains the WASM memory and the stable memory of every canister. That's the main part of this subnet state. But because it's replicated, it means that any update call that changes the state has to be processed by all the replicas, while query calls that don't change the state can just be answered by one of the replicas. And of course, at the end, everything is controlled by the network nervous system, including what replicas are in what subnet and what software version runs on these replicas. a bit more on like how we maintain that state. We generally operate in blocks. So if you send an update message to a subnet, then the consensus layer groups those messages into blocks, and then a block of messages is executed against the state, which gives you a new change state. And this process of generating a block, executing it, generating a block, executing it, happens at a rate of 1 block per second. And in fact, it happens on all the replicas in parallel. So each replica will have the same block and apply it to the same state and do it in parallel. Now, if everything goes right, this is kind of the end of the story, because all the replicas would have the same state at the same time at all times. However, of course, things can go wrong. A replica could simply crash, for example, or somebody could even just plug out a replica. As you remember, somebody else has physical access to these replicas, the node providers. So to handle this, we need more safeguards. And one of these safeguards are the so-called checkpoints. So checkpoints we create every 500 blocks. And what they are is they are a copy of the state, but the difference to the normal state is that the checkpoint is on the hard drive of the replica, whereas a state is at least partially in the RAM. These checkpoints, they have two main functions. So the first one is that if you have a checkpoint, you can continue from there. So if a replica just crashes and restarts, it will of course have wiped its RAM, but it will still have the latest checkpoint on disk, and it can continue from there. The other reason why we have checkpoints is it's an opportunity to make sure that the replicas do indeed have the same state and not somehow different from each other. So that's why once we have a checkpoint, we compute a hash of it, and then we make sure that all the replicas have the same hash. And if they do have the same one, to be more precise, just 2/3 of the nodes need to have the same one to reach consensus. If you do have, we create something called the catch-up package, which is just a proof that that a checkpoint is valid and shared by all the replicas. Now, it's, however, also possible that a replica simply falls behind. So if somebody pulls the plug on a replica and then half an hour later pulls it back in this half an hour, all the healthy replicas will have continued producing blocks at 1 block a second. So now when the replica comes back online, it will have a checkpoint on disk, but it's half an hour old. So in this case, we need some process where a replica can rejoin the subnet. And this is in fact where state sync comes in. So if a replica tries to rejoin a subnet, or in fact, even if it tries to join a subnet, a replica might be newly assigned to a subnet by the NNS. In both cases, the process is the same. First, it needs to get the most recent cup, which contains a lot of interesting cryptography, first of all, which unfortunately is outside the scope of this talk. But it also contains some metadata about the most recent checkpoint. In particular, it contains its height being just the number of blocks processed, and a hash of that checkpoint. What it doesn't actually contain is the full state. And as long as you don't have the state, you cannot contribute to the subnet. You cannot answer a query because you don't have the state. So state sync is the next step in that. It's a protocol where a replica that is trying to rejoin can fetch the full state at the full checkpoint from the healthy replicas so that it then can run with from that. It's not quite the last step in a rejoin, because while we are doing state sync, and that can be minutes, in that time, all the healthy replicas will produce more blocks and execute them. So by the end of state sync, we will have a checkpoint, but it will be slightly out of date. So the last step of a proper rejoin is that we have to replay all the missed blocks as quickly as possible so that we, at the end, have a state that is exactly the same as all the other replicas. So let's look at kind of example where we had some problems with that. And this is from last November on one of our subnets, which is called jtdsg. So you might have seen subnet names are these really long strings, but we have one that starts with jtdsg. By November last year, its state size grew to 170 gigabytes. And in fact, in the meantime, it's way past that already. But in November, it was 170. And it's by far our largest subnet. It contains, among others, the Sonic decks, but a lot of other canisters as well. All other subnets are under 100 gigabytes. Now, what happened in November is that one of the replicas fell behind. And as it tried to catch up by doing state sync. However, the time difference between a healthy replica writing the checkpoint to disk and the end of state sync was a whole 15 minutes, meaning by the end of state sync, the replica was still 15 minutes behind. And that was just too much to catch up. So what happened in this case was that it just started a new state sync. In fact, the healthy replicas already produced a new checkpoint in the meantime, because if you remember, I said we produce 1 block a second and the checkpoint every 500 blocks, meaning it takes roughly 8 minutes between checkpoints. So what happened is after 15 minutes, we just tried to state sync the next one and we ended up in an infinite loop and we could never actually rejoin. And this is, of course, the problem. We can't really have replicas fall out and not being able to rejoin. Now, in November, our immediate fix was to reduce the finalization rate of the subnet. So what that means is that instead of producing 1 block a second, we just produce 1 block every 2 seconds, basically slowing the whole subnet down. And in fact, as soon as we did that, the state sync was able to catch up again. But of course, that's not the proper fix because it has a lot of drawbacks. And in fact, if you're a user of that subnet, you would have noticed that everything is slower. So the proper fix of these problems is that state sync should really not take 15 minutes. So I'm going to talk about what we did to get it down from 15 minutes here. But first, let's break state sync down a bit more into components. So there are 3 main parts to state sync. The first one, which is on the top left of this picture, is we have to write the checkpoint to disk. So we take a state which lives in memory, or at least partly in memory, and we write it to disk. This is step 1 in the process. The next one is, as I said earlier, we would like to compute a hash of the checkpoint so that we can compare it between the different replicas and make sure it's the same. And this hashing step, this hash we call the manifest. So we, in fact, break it down a bit more. We don't just compute 1 hash of the whole state. We subdivide the checkpoint into chunks of 1 megabyte each. And we compute a hash of each of these chunks. We'll see later why we want these chunks. So here on this slide, there is actually an example. We have a file.memory.bin. So this would be the heap memory of 1 canister in this subnet. And in this example, it has three chunks. Once we have the manifest, first of all, we take like an overall hash, we put that into a catch-up package and reach consensus over it. The other thing we do is we advertise that we now have a state. So we send a message to all the other replicas and say, I have a checkpoint and a manifest at height 9. Here is its hash. You can download it if you want to. But in fact, if all the replicas are healthy, that's the end of the story, because nobody needs to state sync if they're all healthy. Now, if one replica did fall behind, that's when actual state sync kicks in. So what happens there is we want to download the entire checkpoint from another node. Now, transferring 230 gigabytes or whatever the state size is over the network is a huge waste. Even though we have 10 gigabit, most node providers have like 10 gigabit internet connections, that still is way too wasteful to try to transfer everything over the internet. However, we are in the luckily, we don't actually need to, because chances are, if the node fell behind because it was offline for half an hour, in this case, it does have its own checkpoint. It's just half an hour too old. But what we can do is most of the state wouldn't have changed in this half an hour. For example, if there is a canister that has static assets, it most likely wouldn't have changed them within the last half an hour. So what we do instead is we fetch the manifest of the updated state, we compare it with the manifest of the state that we have, and all the chunks that haven't changed between the two manifests, we just copy over. So we go into our old checkpoint and we just copy it into our new checkpoint. And only the chunks that have actually changed, we then fetch over the internet. And for the actual fetching part, you can think of like BitTorrent as like a model. So it would just ask for chunks from all the healthy replicas at the same time. So on our favorite subnet, jtdsg, the amount of time it took looked like this. So checkpoint writing 4 seconds, which is still okay. Manifest computation 6 minutes, and state sync itself 9 minutes. And somewhat awkwardly, most of these 9 minutes were spent copying files and not actually fetching over the internet. And in fact, the goal of this talk, or all the improvements in this talk, is going to be to reduce these numbers to something much lower. So let's talk about the actual optimizations that we did. There are 8 in total that I'm going to talk about, and I'm not going to go over them one by one on this slide. We will go over them one by one in the next few slides, but I want to point out they kind of fall into a couple of categories. So first of all, they are about checkpoint writing, manifest, and state sync, all 3. But some of them are just about doing work more efficiently. Most of them are in fact about using multiple threads, where previously we just did it single-threaded. A second category of improvements are more algorithmically. Sometimes we compute something that we really don't need, so we can improve it by not computing that something. And the third category is, it's a bit different. It's we ran into a few issues where it's not really about speeding up state sync. It's about, if we get to a certain situation, state sync would just never finish. And so we also fixed those. Yeah. So let's talk about the first improvement. This is about checkpoint writing. So the idea is that instead of doing it single-threaded, as we did before, we just use multiple threads. So the main work we have to do in checkpoint writing is we have to go over our data structures, see what data is only in memory but needs to be written to disk, and then write it to disk. And turns out doing this in a multi-threaded way gives us a 4 to 5x improvement. You can in fact see the graphs on the bottom right. So our subnet jtdsg, you can see where, so the graph shows the time it takes to do checkpoint writing just before and just after the upgrade, so when the upgrade was rolled out. And you can see it falls like a cliff from around 4 seconds to 1 second. Now, you might say saving 3 seconds out of 15 minutes isn't really that amazing. And I guess you're right. But you see the real power of this change you can see on other subnets. So we have another subnet which it distinguishes itself by having a lot of canisters rather than a large state. And there, in fact, the checkpoint writing time went from 25 seconds to 5 seconds. So it made quite a big amount of difference. Yeah. So I don't want to say too much about this because it's clear if you can do it faster, it's better. The next one is about the manifest computation. So it's the same idea. Manifest computation, we can do it in a multi-threaded way. During the manifest computation, the main work is reading a chunk from disk and then computing its hash. And of course, computing a hash is a very CPU intensive operation. So it makes sense that multi-threaded, there is room to grow if you do it multi-threaded. And in fact, it turns out it's like 2 to 3x for the manifest computation. The next improvement to the manifest computation is a bit more involved conceptually. So we create checkpoints and compute manifests every 500 blocks. So that happens every 8 minutes or so. Now, just as we discussed earlier, for state sync, in like an 8-minute window, not that much of a checkpoint would have changed. So it is a bit of a waste to recompute the hash of a chunk multiple times, even if it doesn't change. So the idea here was to not do that. We already keep, for other reasons, a list of chunks that changed since the last checkpoint. So which data structure we call the dirty pages. And in fact, based on that, we know which ones. So once we know which chunks changed and which ones didn't, for those that didn't change, we can just take the hash out of the last manifest and just reuse it. Of course, for those chunks that did change, we do have to recompute the hash. Now, we didn't quite want to go as far as always do that, like never recomputing a hash that didn't change, because we are a bit afraid that some bit flips somewhere on a disk, like some hard drive gets hit by a cosmic ray and suddenly the state is corrupted. It would be very bad if we then just propagated that error indefinitely to future checkpoints. So what we ended up with is some sort of hybrid where we, of course, compute the hashes that changed, and we also compute 10% of the rest. And but the nice thing about this incremental manifest computation is that now the time it takes to compute the manifest is no longer a function of the size of the state, which, as you remember, 200 gigabyte. It's now a function of the changes since the last checkpoint, which in practice on jtdsg is a couple of gigabytes usually. And here we see what this does to the manifest computation time. So what we're looking at is a graph that shows the time it takes to compute the manifest on one of the replicas on our subnet, starting in November and ending in February. You can clearly see so it starts at 6 minutes. And as soon as the software upgrade that introduced parallel manifest computation was rolled out, it immediately dropped to around 2 minutes. And then later, after Christmas, when we rolled out the incremental manifest computation, it dropped to around 15 seconds. So it went from 6 minutes to 15 seconds in the span of 2 months. So this is what I want to present about manifest computation. Now let's move on to actual state sync. So let's talk first a bit about where we spend the time in state sync. There are kind of two cases. If we don't have a recent checkpoint, for example, because we just joined the subnet, then there is not much we can do. We have to fetch the entire state over the network. The network is slow comparably. So that's just going to take a while. It's in fact the other case where we can improve a lot. So if we do have a checkpoint, most of the chunks will be copied. And turns out this copying step we did in a somewhat silly way. That was wasteful. So the basic steps to copy a chunk is before our changes would be read the chunk from the old checkpoint, verify that it's correct by computing its hash and comparing the hash with what's in the manifest, and then write that chunk to the new checkpoint. Now, you might ask, why do we have this verify step in the middle? And this is because we actually got burned there. We didn't always have that. But then last summer, we had the problem that a replica crashed. It corrupted the checkpoint on disk. And then we just happily copied it during state sync, leading to further problems. So we do want to verify its hash to protect against corruption. Now, there are a few things we could improve. We were able to improve there. The first one is same as before. Let's do it multi-threaded. Yeah, not much to say. Just throw more threads at the problem. And that gave us like 3x improvement already. The second one is it's a bit of an equivalent to incremental manifest computation. So I did justify our verification step by saying that there could be I/O problems that we want to detect. However, this is kind of a special case that happens occasionally. What we're really worried about is that something like happened to jtdsg happens, where we do state sync and then immediately another one and immediately another one and immediately the other one. In those cases, it really doesn't make sense to verify every time. So what we're doing now is that instead of always verifying a chunk, we verify a chunk the first time we do state sync. And then if it happens immediately after, we don't verify. Because we just did, in fact, verify it 10 minutes earlier. So this way we save us the hassle of verifying and, in fact, save time with that. Now, the last improvement to the speed of state sync is, so one problem we still have is that what we do is we read the chunk and then write it back. Now that doesn't quite play well with our file system, which is XFS. XFS has a feature called copy and write. Now, what copy and write does is it's pretty cool. If you tell it to copy a file, it doesn't like duplicate the bits of that file and have it twice. What it will do is it will just keep the file once and point to it twice. And if at a later point you change one of the two files, it would only then like keep them separately. And that's a pretty cool feature because it means that if you tell it to copy a file, it'll basically be done immediately. Now, if you do what we did of reading a chunk from one file and then writing it to another, you completely circumvent the smartness of the file system. So the answer to that is not do that. So instead of reading and then writing, what we now do is we call a system call called copy file range, which does basically what it says. So you tell it, please copy this range of this file to that range of that other file. And if you do that, XFS can in fact speed things up by just pointing to the same chunk twice. And what's particularly powerful is this combination of copy file range and no verification. Because if you do both of those, there's no need to read the data at all. All you need to do to copy the chunk is you give it one call to copy file range, and the file system does the rest. Now, it turns out that if you do both of them, the entire copying phase of state sync is now 2 to 3 seconds for a large state. And if you remember, we started at 9 minutes. So we went from 9 minutes to a couple of seconds. Although the 9 minutes included fetching, while this 2 to 3 seconds did not, but yeah. So yeah, this is the last of the changes that speeds up state sync. Now there is another problems we run into, and this problem is about how checkpoints are deleted. Now, in the normal running of a replica, there is no reason to keep an old checkpoint. All you need is the most recent checkpoint, so that if you crash, you can continue from that one. All the checkpoints you can just delete. However, that's a problem if you do state sync, because there might be a replica that is trying to catch up by doing state sync, and then suddenly all the other replicas, the healthy ones, just delete the checkpoint off their disk. So, and then of course it cannot continue downloading that. And this could potentially lead to aborted state syncs that will just not be able to finish. Now, to fix that issue, we kind of have two solutions that both kind of fix it. The first one is, let's just keep a few more checkpoints around. So we changed it so instead of only the latest checkpoint, we keep the last 3 checkpoints. That gives us more time to do state sync if state sync in fact happens. It still doesn't fix it completely, right? Because it could take longer than that, but still it makes the likelihood of running into this problem smaller. Now you might wonder what this does to our disk usage. Are we running out of disk if we do that? And luckily we don't, because what we discussed earlier about XFS. So if you the 2 checkpoints will be mostly the same, so they will mostly only exist once on disk. And it's really surprising how little of an overhead it is to the disk. So this is one fix. Of course, doesn't fix it completely, but it makes it less bad. The other fix is trying to make sure that if a state sync really aborts because of that, we should still be able to handle it. And so we did some tests and see if we can handle it like without any changes. And turns out we don't really handle it very well. What happened before was that we would do state sync until at some point it aborts. And then we would just try to do state sync for the next checkpoint, completely throwing away all the work we did before. Now, the problem is if you try to download, let's say 200 gigabytes from the replica and you run out of time, and then you just try to download another 200 gigabytes, you'll run out of time again. In fact, you can see that in the graph at the bottom in the before picture. So this is a metric called state sync remaining bytes. So it's a progress bar for state sync. If it reaches 0, it would be successful. But you can see it downloads a couple of chunks, and then at some point it aborts and it just jumps back up to the top and retries, and it would just never finish. I should say this graph is not from production. We luckily never ran into this issue in production. But so what we did as now to fix that is, it really doesn't make sense to download parts of a state and then just throw it away afterwards. So what we do now instead is, when we have an aborted state sync, we put it into a cache. And then when we try the next state sync, we copy from it. Just like earlier, we copied from a checkpoint. We now just copy from the cache. And this way we continuously can make progress, which we see in like the after picture. So we make some progress, and then once in a while it spikes up. That's when a new state sync happens, and we have to copy for a while. But we continuously make progress, and in fact, at the very end, we do manage to do a state sync. So this is the last of these improvements. So here is the list again. So I just want to kind of stress again that this is really just one example of us working on like the fundamentals of performance and scalability and so on. There are many more, and in fact you can look forward to more community conversations about improvements like that. but yeah, at least now state sync seems to be less of the bottleneck than it was before. So before I'll finish, here is a list of engineers who worked on this, and thank you very much.
Cool. So thank you so much, Stefan, for that enlightening overview. So if anybody from the audience has any questions, now is your chance to be able to ask questions to Stefan. Can be on this topic. And I know we have other Dfinity people on the call. So if you wanted to chat about something else, definitely let us know. I don't think I saw any questions that were dropped into the chat during the course of the overview. So I take it that Stefan's explanation was crystal clear and that everybody understood everything. Okay, Matthew in the chat has a question. Will this become part of the documentation, Stefan?
I'm not quite sure what we do have documentation about the replicated state, which is this kind of falls into. I don't think the individual improvements will really feature there, but I'm not quite sure what the status of these documents, but we definitely do have documentation on like how replicated state works. We also have documentation on how like catch-up packages work and so on. But yeah, so I'm not quite sure. I didn't add any of that to any documentation, at least so far.
Cool. Thank you, Stefan. Cool. So if there aren't any additional questions, we're going to wrap up the call for today. So last call for any questions, burning questions you guys have. You can feel free to put Stefan in the hot seat, or you can be nice and let him off the hook. Okay, I think that there are not additional questions. If there are questions, I'm going to drop my Twitter handle into the chat here. So you guys can always DM me on Twitter, and I'm happy to pass on the questions to Stefan or any other speaker for community conversations. Thank you so much, Stefan. Once again, thank you for our audience for tuning in, and see you guys at a future community conversations. Bye, everyone.